Hello and welcome to lecture 48 of the course Theory of Computation. In the previous lecture, we saw the verifier characterization of NP. In this lecture, we'll first see polynomial time reductions, right? And this will later be helpful towards establishing the notion of NP completeness, right? So let's get into the definition of polynomial time reductions. So we have already seen reductions earlier, which was in chapter 5, mapping reductions or many one reductions, right? So this is similar but with a different constraint on the machine that computes a reduction, right? So what is a reduction? So first I am going to define polynomial time computable function. So we say that a function f is polynomial time computable if there is a deterministic Turing machine M that takes the input and provides the output. Meaning, that is, so the function f is polynomial time computable if there is a polynomial time deterministic Turing machine M that takes the input, let's say w, and outputs fw on the tape and then stops. So there should be a machine that takes w as input and outputs fw, and this should be done in polynomial time by a deterministic Turing machine, right? So this is the definition of polynomial time computable function, and we say that a language A is polynomial time reducible to language B, right, and denoted by this notation A less than or equal to B and with a P subscript to the less than or equal to, if there is a polynomial time computable function f that constitutes the reduction, right? So what do I mean by reduction? The reduction is that for all w in A, f of w should be in B, and for all w not in A, f of w should not be in B. So in short, w is in A if and only if f of w is in B. So this is very similar to the notion of mapping reductions or many one reductions that we saw in chapter 5. The only difference is that so even there we had this w is in A, then f of w is in B. The only difference is that here we are insisting that the function that constitutes the reduction, the function f, should be polynomial time computable, right? So this is what I am highlighting. This function should be polynomial time computable in the case of a polynomial time reduction. Whereas in the case of mapping reduction, we just want it to be computable by some Turing machine, right? Not we want it to be computable by some Turing machine, but here we are saying that it should be computable by polynomial time Turing machine, right? And the rest is standard. Like suppose there is a the function is from sigma star to sigma star, and any w that is in A gets mapped to some w that is in B, right? And any w that is not in A gets mapped to some w that is not in B. So A maps to B and a complement maps to B complement. Okay. So the goal is, given a situation, given a string that we don't know whether it is from A or whether it is in A or not, we want to transform it into the domain of B. Right? And suppose we know how to test the membership in B. So we don't know how to test whether some string is in A or not, right? It could be in A or it could be in A complement. But we know how to test a membership in B. Then we can transform the instance. We can basically, given w, we can compute f of w and then check whether f of w is in B or not, right? So if f of w is in B, the only way that f of w could have been in B is if w was in A. And if f of w is in B complement, the only way that we could come to B complement is if w is in A complement, right? So testing whether f of w is in B or not is as good as testing whether w is in A or not, right? So that is the main goal of this reduction. But the main difference here from mapping reductions is that now we are putting time constraints, or we are putting resource constraints on the how to compute the f, right? Which is kind of not that surprising if you think about it, because we are in the chapter that pertains to time complexity, right? And we are dealing with complexity classes that do calculation as per time complexity. So we need some handle on the we need some handle on how much time it takes, otherwise this could become meaningless. So I'll explain that in a bit, right? So the goal, as I mentioned, is suppose we are given a w, right? We are given some w and we want to determine whether it's in A. So the way to do it is we transform it to B, we compute the function, right? And then check whether the function is in B or not, right? So transform A to B means compute f of w given w and then use the decider of B to decide B, right? So later in a bit we'll see the following, that suppose A is reducible to B in polynomial time and suppose B is in P, this will imply that A is in P, right? So this is going to be one of our main results that we will use. Suppose A is reducible to P and B is in P, then A is also in P, right? This is, so if you recall, we had this statement in chapter 5 that suppose A reducible to B in A mapping reducible to B and then B is decidable, this implies A is decidable. This is something analogous to that, right? And the point that I want to say is that this restriction is important, right? This restriction is important. Right. So suppose we did not have this restriction of polynomial time computable, right? Then let's say we could take exponential time to compute this function, right? Then the problem is that let's say we are given a 3 coloring instance or a satisfiable instance. Then if I don't have any time bound, then I could try out all the possible 2 power n assignments. Let's say this is satisfiability, right? So I'll tell you how to compute a reduction, right, to a language, and the resulting and the testing of the second language will be polynomial time, but the original language is something that we do not know whether it is in polynomial time or not, right? So suppose we have a sat instance, right? What I can do is to compute exhaustively all the possible assignments and then basically decide sat, right? And then I output the function value, right? So the function value is going to be 1 if the formula is satisfiable and 0 otherwise. So I just take 2 power n time and try out all possible assignments, right? And then basically I have decided whether it is satisfiable or not. But since my goal is to compute the reduction, I will output 1 if it is satisfiable and 0 otherwise, right? So now this gives us a reduction, right? This gives us a reduction, although a very silly reduction. So any formula that is satisfiable will map to 1, and any formula that is satisfiable will map to 1, right? And any formula that is not satisfiable will map to some other string, will map to 0, right? So basically this is a reduction from satisfiability to the set 1 and everything that is not 1, right? And then this is easy to decide. It's easy to decide whether so suppose the transformed instance is quite easy to decide. So now you see that, our goal was to efficiently decide a language A, right? So which means all the steps should be efficient. I should be able to efficiently compute the transformation and efficiently decide B, right? So basically both the steps here, the transformation from A to B, this should be efficient and the decision of B should be efficient. Now if this transformation is not efficient, if I am allowed infinite time, right, then the whole thing is not really meaningful, right? So like we have here, I could easily, if I am not restricted in the time, I could easily compute the reduction from sat to some trivial language like 1 and 0, right? And it's easy to decide this. Easy to decide between 1 and 0, right? So now we have reduced sat to a language that is easy to decide, but then the reduction takes exponential time. So we cannot basically hide the complexity of the problem in the reduction. That's why we have we have to impose, to make this whole thing meaningful, we have to impose a time restriction on the time that is taken for the reduction, right? So otherwise it leads to such meaningless results, right? So now if you impose such time restrictions, then we cannot do this restriction, we cannot do this reduction from SAT to like the 0-1 language, right? So that is the point here. So for instance, we cannot replace this by a mapping reduction, because then we cannot infer that A is in P, right? Because the reduction itself may take exponential time. So then how can we infer that the whole process is in polynomial time, right? Okay, so now let's come to the proof of the statement that I mentioned over here, that A reducible to B in polynomial time and B is in polynomial time implies A is in polynomial time, right? So the idea is whatever we have already discussed. So suppose M is the decider for B. Okay, M is the decider for B in polynomial time. We can construct a decider for A as follows. We first compute the function, the reduction from A to B, right? So F is the reduction. Assume F is the reduction. Maybe I'll just write that. Assume F is the poly time reduction. Right. So we first compute F and then we compute the reduction, right? Compute the reduction F, and then we check for the membership in B. So we use the decider for B. We basically run M on the reduced instance, which is f of W, and that's it. And if M accepts f of W, we accept W. If M rejects f of W, we reject. So the correctness is straightforward, right? Because only strings in A will come to B. And these strings will be accepted, and those strings that are in A complement will come to B complement, and those will be rejected. So the correctness is straightforward. So the time complexity, let's just check the time complexity. Suppose f of W takes to compute f of W takes, let's say, n power k1 time, right? Which means this step takes the computing f of W takes n power k1 time, where n is the length of the input, right? Where n is, let's say, n is the length of the input. Now let's say, suppose M takes or M runs in like f of W, whatever is the input length to the power k2 time, right? So the input to M is f of W, right? Suppose the exponent of M is k2, right? So we know M is a polynomial time Turing machine, so it will run in something power the length power k2 for some constant k2, right? But what is the length of f of W? So we know only the length of W, right? What is the length of f of W? So thing is that the only thing that we know about f of W is that it is produced by a Turing machine that runs in time n power k1, right? So which means in that time it even has to write the output. So the length of f of W cannot be more than n power k1. If it is more, then writing the output will take more time. So we can say that since time taken for the reduction is n power k1, we have the length of f of W also should be at most n power k1. right? Which means m takes n power k1 whole power k2 time. Which is n power k1 k2. So this step takes n power k1 k2. So the total time taken here is n power k1 plus n power k1 k2. So the second part is that this is the dominating thing, n power k1 k2, which is okay, but this is still a constant. This is still, the exponent is still a constant. So n power k1 k2 is still polynomial in the input length, where the input is the string w, right? So the decider takes, so the A decider takes n power k1 k2 time. So this is polynomial time, polynomial in the length of the input, right? So that's the proof. So the proof is very simple. We convert A instance to B, and then we run the B decider on the reduced instance, and the correctness is quite clear, and the running time for the whole process is the running time for the conversion, which is n power k1, and the running time for running the decider on the reduced instance, which is the length of the reduced instance power k2, which turns out to be n power k1 k2. So the whole running time is n power k1 k2 plus n power k1, which is dominated by n power k1 k2, which is a polynomial time in the length of the input. So hence A is in P, right? So we have given a decider for A which runs in polynomial time, right? And what I said before, the proof is complete. What I said before is that if we did not have this restriction, right, that the reduction from A to B is in polynomial time, we cannot get this, we cannot infer this, because this first step itself would have taken, could have taken more time than polynomial. Okay. Now some briefly some other results that I'll mention, right? Some other results that I'll mention. One is that the same thing, if A reduces to B in polynomial time and B is in NP, then A is in NP. This is true because if A reduces to B and B is in NP, then A is in NP. So basically these two should together imply an NP decider for A, which is straightforward by the same process. So we compute the reduction and then run the non-deterministic decider for B on the reduced instance, right? So that together they get a non-deterministic decider for A, right? So the claim is that A is in NP, right? So if B is in NP, then that gives a non-deterministic decider for A. The next thing is that if A reduces to B and then A is not in P, then B is not in P, right? So the analogous result here is what we saw in chapter 5. If A was mapping reducible to B and A was undecidable, then B is undecidable. Why is this true? So suppose this is not true. If A reducible to B and A not in P, suppose B was in P, right? Suppose B was in P, then together by this theorem it would imply that A is in P, which is a contradiction, right? So if A is not in P, then B should certainly be not in P, because if B was in P, then that gives a way for us to decide A in polynomial time. So if A is reducible to B in polynomial time and A not in A not in P, that implies that B not in P. Again, just to the analogous results where if A was mapping reducible to B and B was decidable, A was decidable, right? And the analogous result for this is that if A is mapping reducible to B and A is undecidable, then B is undecidable. The next thing is transitivity, right? So suppose A reduces to B and B reduces to C, then A reduces to C. Why is this true? Because we could just take the composition of the two reductions. So suppose this is A, B and C, and the function f takes you from A to B and the function g takes you from B to C. And we can compose these two functions. You can take f of g or you can take g of f to compute a reduction from A to C, right? So g of f gives a reduction from A to C, right? Because so we compute given w, we compute f and then g of f of w, right? And the correctness is easy because anything that is in A goes to B and that goes to C, and anything that is not in A goes to B complement and that goes to C complement. And the time complexity is also not that difficult to see. Basically, we want to say that the time composition, or sorry, the time complexity of computing the composition is also polynomial in the length of the input, and that the reasoning for that is similar to the way we argued the time complexity of this theorem, this n power k1 k2. So this you try out as an exercise. Computing the correctness is evident, and the time complexity is similar to the proof of this theorem. And finally, one more thing that I want to say is, if A reduces to B in polynomial time, A complement reduces to B complement. Basically, the same reduction function does what we want, because anything from A complement maps to B complement, anything from A maps to B. So the same function serves as this reduction as well, right? So these are kind of standard facts. But try it out and try to prove these things and try to write down this and prove it formally. I have given you the proof, at least orally I told you the proof, but to get some practice you may try to write down the proofs yourself, right? So that completes the definition of polynomial time reduction, right, and some properties.